Okay, so good day, everyone. On behalf of our small international team, in next half an hour, I will present a research GPU compiler project, which is partially developed here in the University of Lugano. So the modern GPU computing has been around already for 5 or 6 years, and out of this period of time, almost for 5 years, the only two technologies existing for GPU development were CUDA and OpenSEC. And if you ever ported any large existent application on the GPUs, you might know that in many situations it would yield at least to significant code rewrite, or in many cases even rewrite from scratch. And it has been a large obstacle for porting onto GPU of the existing complex applications. Fortunately, recently the situation started to change because different compilers groups started to think about how we can generate the GPU code in the background, considering the original source in C or Fortran. And the currently most popular technology of this kind is OpenACC, which stands for a set of specific annotations or directives to existing programming languages like C and Fortran, which could be used by a developer to mark up the regions of code that should go on GPU and different data properties. And by compiler, these directives are used as hints to generate GPU code underneath. Unfortunately, OpenACC still has a lot of limitations. Although it's a good step forward, it is still a very limited solution. I will show you some examples. So the goal of our research project is to make another step ahead and consider what things could be improved to make even more robust, even more usable GPU code, automatically GPU code generating compiler. So this presentation is mostly intended for potential users, so we can now directly jump to some simple examples. So here we have a simple example of Fortran program, which is doing some computations in large 3D loop. So what KernelGen can do about this? In case of usual Linux environment, you will probably compile this program with G-Fortran or some usual compiler. So in case of KernelGen, you just need to use KernelGen G-Fortran, and you will get also a binary, but that will be a hybrid binary. Hybrid binary in that sense that if you will run it normally, you will have it running on CPU. And in case if you will add an environment variable, you will have it running on GPU. Note the large performance difference. Same example for C, same commands to compile and execute, same benefit in performance. So this is a very simple example just to show you that it works. But it would be more interesting to look how we can improve current OpenACC compiler's limitations. I think two most important limitations of OpenACC are currently the absence of external call support and poor pointer analysis. Let's see the examples. So by external calls, we mean that if in previous examples you would have a loop which is doing some computation dependent on functions defined in some other compilation unit, this code, although it could be parallel, it will not be parallelized because OpenACC considers all the GPU analysis as per unit. So all source files must be self-containing. So in case of PGI OpenSEC, you will get this kind of message, and code will not be parallelized. In KernelGen, we are taking all the decision making to the link time and runtime. In the link time, all such kind of dependencies are resolved, and the actual GPU code is generated in runtime when the application is running, like JIT compilers, like Java. So in this case, we are able to parallelize this code. We can parallelize this code even if the used function is in the static library, which could be very useful for large codes structured into multiple libraries. I believe the external calls are very serious limitation because many complex applications are structured into blocks like classes or models, which are supposed to call and use each other. And it seems like OpenSEC is not yet ready for this configuration, but it's not so hard to implement it. Okay, so another problem is pointers tracking. So for pointers tracking, we can consider such an example with 3 array pointers coming as an input from somewhere we don't know their origin and can't track it. And these pointers are used also in 3D computational loop. So from the compiler point of view, there is a problem here because we cannot reliably determine if these 3 pointers are referring to the independent memory regions or if the memory regions are intersecting. Depending on the situation, if they are parallel or if they are independent, you can parallelize this code. And if they're intersecting, you will not be able to parallelize it. Certainly, in most of the cases, developers assume that these pointers are not intersecting, but compiler is a reliable tool. It must know for sure. For this reason, there are some warnings, and finally, this loop will also not be parallelized. In case of KernelGen, we have all the final decision making about parallelization in the runtime, and for this reason, we can additionally use the runtime context information. Runtime context means we can substitute the actual values of pointers and dimensions and just make a simple comparison of memory regions with known intervals. So this is some kind of initial representation of loop in our compiler, and this is some debug output from memory ranges analysis. So everything is fine in this case, and this loop is also parallelized. Okay, so besides limitations, there are also some nice features, not really limitations of OpenSEC, but still very nice features for developers. For instance, handling different forms of loops not limited to arithmetic 4, like in OpenSEC. We can also parallelize implicit loops from Fortran, and we can parallelize loops with pointer arithmetics in C and C++. So why we can parallelize while loops? The reason for that is that the internal engine behind KernelGen is LLVM. In case you have heard of it, it's now a very popular compiler infrastructure, and its internal representation is very close to, well, it's kind of close to assembly language. And in terms of this format, all loops, regardless their high-level kind, are lowered to the same low-level form, like loop header, body, phenode, and induction variable. And it may happen that even while loop will fit the notation we are searching for in the low-level format. And this way, while loops can be parallelized in some cases in the same way as for loops are. Fortran vice array, by Fortran vice array code, I mean such kind of collective statements. Here, that C1 and C2 are arrays of complex numbers, and this statement means we are applying this operation to each element of all arrays. front end, we use GCC for front end, expands this statement to the plain loop internally. And since we are not source-to-source compilers, since we are working with intermediate representation, we can also parallelize this loop, just like in first two simple examples. Same thing for pointer arithmetics. Since we are working with low-level representation, we actually don't have any kind of arrays indexing in our view. All array accesses to us are pointer accesses. For this reason, there is no difference between indexing, accessing arrays with indexes and accessing arrays with pointers and shifting pointer on every iteration, like it's showed here. And for OpenSEC, by some reason, even standard states that pointers arithmetic is not supported. So in our case, this is also parallelized. Okay, so I hope our language features are a little bit impressive. Now, what about performance? So for performance testing, we have internally test suite of 14 different test cases. Test cases are computationally different, but they all follow the same general algorithm, which we consider currently the main goal for our project. It's it's very similar to time explicit numerical solver, like finite differences or whatever. So here we have an outer iteration, outer time iterations, which are not parallel, and inner spatial iterations that could be 2D or 3D on simple regular grid in this case. OpenSEC, in case of OpenSEC, we have pre-allocation of GPU booters and preloading of initial conditions before the first iteration. All the iterations are performed in GPU memory without loading or offloading after every iteration. And finally, in case of OpenSEC, we are offloading back the result from the topmost time slice. Result correctness is checked by computing means norms for output data in different cases in CPU, OpenSEC, and KernelGen. So this graph presents performance difference between KernelGen and PGI OpenSEC. So this chart means by how faster KernelGen is than PGI. So for example, for gradient test case, we are about 60%. Our kernels generated by KernelGen are about 60% faster than kernels generated by PGI. And this situation is quite common, not for all test cases, but for most of them. For instance, we are currently worse on matrix vector multiplication, matrix, and sine cosine. So matrix cases are very well analyzed to this moment. And the reason is that LLVM misoptimize, under-optimize the reduction idiom. The stores are not cached on register, and this is the reason we are slower here. But this problem could be solved quickly, I think. In case of sine cosine here is the only function which is using GPU math functions from this row. And I think since we are compiling GPU math functions also with LLVM, there could be also some minor optimization issues. But note that the worst case is minus 40%, and the best case is about 60%. So both commercial technology and open source based technology are on the same row. Yeah, just for check, we also made a comparison with CPU, but this is nothing interesting. So it's just accelerate with some big numbers. These are absolute numbers of speed up. I think it's more reasonable to compare two technologies of the same kind, like KernelGen and PGI. Please note that we are not using any kind of directives, any kind of annotations. We receive code like as it is. and it may contain both parallel and non-parallel loops. For example, in this case, we have the outer loop parallelized and the inner loop not parallelized because it is reduction. Technically, it would be possible to parallelize the reduction, but at the moment, we are not supporting it. Another test case is MPI nesting. So, like in Axel's presentation, we are using CUDA visible device environment variable to assign every MPI node with the GPU, or original version was working on one CPU core per MPI node. So in this case, we don't have any modifications in the program. Program here is the test program match filter application. It is just MPI parallelized, the same one, just MPI parallelized. And seamlessly, KernelGen allows to convert CPU node into GPU node, and the additional level of parallelism will be added by the compiler by means of realization of loops inside MPI program. In case of commercial compiler, you need to pay about $1,500 for one license. In case of our project, you don't need to pay anything because all the components it's assembled from are freeware, and most of them are open source. So here, GCC and Dragon Egg are two tools we use for front-end side to convert the high-level language into the LLVM internal representation. LLVM optimizations, polyhedral analysis, and our own runtime library are used to analyze parallel loops. And NVIDIA's NVPTX backend, also part of LLVM, is used to emit the PTX assembly from the final version of LLVM code. And then it is changed to the CUDA driver stack. The use compiler pipeline is as usual. Please note we are a real compiler, not source-to-source compiler. We have compile time, link time, and runtime parts. But what is unusual is the structuring of different steps between these factors. Specifically, we are taking the final decision-making to the runtime. As I previously said, we are JIT compile. We want to expose additional runtime context information for doing better parallelization job. And for this reason, we have final analysis step here and code generation just right at the moment where we approach the particular loop in the code. Another unusual thing is how execution flow is organized in KernelGen. We have, instead of usual active CPU and passive GPU, we have active GPU, which means GPU tries to manage as much things as it can by means of running so-called main kernel, which is one-thread kernel, persistently on GPU during the whole application lifetime. And this kernel is responsible for data consistency between different kernel launches, and it tracks all the activities. So theoretically, CPU is mostly free, and you can shadow another part of MPI job on CPU, except those parts of the code that can't be technically ported on GPU or not efficient on GPU. So if you rotate this chart by 90 degrees, okay, yeah, I already described this. If you rotate this chart by 90 degrees, every KernelGen generated binary program in case of GPU starts with some kind of initialization, then compile and launch the main kernel. And main kernel is alive during the whole application lifetime. But in case if we approached a parallel loop, the execution is interrupted. The kernel is not stopped, but it's interrupted with a callback requesting the CPU side, which is partly the LLVM runtime and our runtime, to analyze if the loop is parallel within current runtime context. And in case it is, compile it for GPU and launch it in parallel GPU stream. So once this kernel compute kernel is finished, we do another callback and resume the execution of main kernel. In this case, the data is seamlessly shared here. Another case would be if we have a system call, a call to external library which we don't have source code for, or some portion of code which is inefficient on GPU. We also do a callback and maybe JIT compilation, but the final binary will be a host binary. And in case this host binary depends on GPU data, there is a page fault handler which lazily loads GPU data on host depending on the need. And when the host call finishes, the dirty pages are offloaded back into the GPU memory, and main kernel also resumes its execution. The key things about our loops analysis pipeline are, as mentioned, substitutions of pointers and integer parameters to determine the actual memory ranges. Then we use the polyhedral analysis tool for LLVM, which can say basically if the loop iterations are dependent or independent. In case they are independent, our contribution to poly is the mapping of sequence of nested parallel loops onto the GPU compute grid. And once we perform this mapping, the final version of LLVM intermediate presentation code is lowered further to PDX assembly and executed on GPU. I think we can have just 1 minute walkthrough through different formats of code generation. So this was our initial loop, for instance. This is the Gimple intermediate presentation used by GCC. By means of DragonEgg, we convert this Gimple, not we, but that existing project converts it to the LLVM. This is the initial LLVM for this function. We make some preliminary decisions about what loops in this function could be potentially parallel without generating any code. So here we have an extracted function with substituted values for pointers and dimensions. And in case this loop has independent iterations, the LLVMer is specialized for GPU code generation. For instance, you can notice here the PDX kernel, PDX device attribution, and a special intrinsic NVVM means NVIDIA intrinsic for obtaining the GPU compute grid position for the current thread. So once we have this final LLVMer, backend converts it to the PDX, and PDX is finally converted to the device assembly for GPU. So currently we have a pretty functional prototype, but it still has several important features not covered. For instance, we have only we support only simple loop indexing, so no negative increments, no non-unit increments, and so on. Currently no support for arbitrary indirect indexing, which is believed very important for such algorithms like sparse linear algebra or structured, unstructured grids. Same issue for OpenSEC, by the way. No support for reduction idiom, and we may still face some minor issues in the parallel code generation because this is a prototype. Yeah, although this is a prototype, it's ready for testing, and in case you would like to test it, you will need just a modern Fermi or Kepler GPU and fresh NVIDIA CUDA driver, and a little bit of patience to follow the build and install guide. The main slide, the purpose of this presentation is this slide. So we want to continue this project further, and in order to do so, we need partners, users, and collaborators. For instance, if you have your program running on CPU, we can assist you to port it with KernelGen onto GPU and deploy on CSCS cluster, for instance. If you have skills in compiler development, there are a lot of interesting proposals and submissions in our project. You may pick up one and contribute or make up your own proposal. And even if you have a completely different view on GPU perspective, but KernelGen still can be useful for you as a framework, we are also ready to help. So this is the download link for this presentation, and in case you have things to discuss, this is our project mailing list. Thank you, and thanks for organizer for accepting us for HPC Advisory Council.